So our next speaker is talking about reinforcement learning overoptimization under distal specification errors. You're going to hear from Manfred Diaz. Manfred is calling in, so you're going to see him. You're going to see his like disembodied face up here. Applause for Manfred.
Awesome. Yeah, sorry guys, I couldn't be able to make it there in person today. Things beyond my control, obviously. But I wanted to sort of like share with you what I've been doing for the past couple of months in during maths, and it's this idea of like reinforcement learning over optimization on the distal specification errors. And yeah, of course, this is a joint work with my mentor Michael Dennis. And we started this project at the beginning of maths with this idea that the problem of like reward specification for reinforcement learning is sort of like a complicated one, because most of the time the question that we need to ask is like, where do the rewards that we use come from? And yeah, that's the origin of the problem of reward specification in reinforcement learning. The problem of reinforcement learning, I think, needs no introduction for this crowd, but it's basically the idea like, given a reward, we try to find a policy that maximizes that reward. And particularly the problem of reward specification is really interesting when you start thinking that when we are reward designers, like when humans try to reward designs, what we're looking for is for this function, this communication sort of device that tries to elicit an agent, a policy from an agent that we actually want, right? We have preferences over the behaviors that the agent might produce, and then we have to select some policies, like in here, some rewards, like in here R and R tilde, that are going to elicit different behaviors for the agent. And the question that reward specification needs to ask is like, how does the designer, his designer, actually knows which reward he has to write in order to elicit a particular behavior from the agent? So that's in a nutshell the problem of reward specification. And what is interesting in this problem is, in some sense, when you look at the structure of the problem, has this bi-level or like Stackelbergian kind of like a structure, where actually the reinforcement learning problem is a sub-problem of the designer problem. So in some sense, when you formulate the reward specification problem, you notice that the designer actually needs to solve a problem that is harder than the one that the agent solves. And we call that sort of like the designer's paradox, because it's sort of like paradoxical than trying to come up with like the perfect specification that elicits the policy from the agent that we actually want. So like it has embedded as a subproblem the problem of that the problem of reinforcement learning, or like the problem that the agents need to solve. So and the main issue that we see with here, and this is why we call this like the designer paradox, or like the interactability of reward specification, is because there is some of like computational rational imbalance, where the problem that of like reward design actually happen in a substrate, most of the time like human mind, like in human designer's mind, that in some sense is different, or like sometimes more suboptimal than where the problem of reward specification actually happens. And exactly this problem, like the human bounded rationality in some sense, is for us at least the cause for many of the reward specification risks and problems that we see every day. And we say, well, like the probably causes of this this kind of like error that we're going to call distal or pernicious specification errors is because human bounded rationality gets embedded into the problem of reward specification. And there are many sources. We are interested at least in three of them. We're talking about rational inattention, or like the capacity to see how the reward affects like different possible states on a really large state space. The idea of like bounded temporal foresight, which is when the designer is sort of designing a reward, is really hard for the designers to compute the distal consequences of those rewards. How does this sum of like cumulative sum of rewards actually ends up affecting the end behavior? And there are a lot of like issues around also like the information processing costs. These are all related to human bounded rationality, and I'm going to show you later how we can actually model this in the context of reinforcement learning. And of course, why we are interested in this is, well, there are a bunch of like different risks that stem from specification errors, and in particularly these problems where the immediate or like proximal preferences of the designer in the short term, like the things that we can foresee, actually, when they're optimized, when they're plugged with reinforcement learning optimization, might lead to particularly dangerous behavior. So we are sort of like selecting a different policy than the one we have, because we cannot foresee the distance consequences of these future outcomes that we're actually writing, but we are unable to compute. So these kind of risks are really important. We have seen like all kind of like or hacking before. The question is, what can we do and what has been done? And at least for us, we use this idea like, well, this is a stack over game kind of like situation, a game between the designer and the agent, to say, well, there is like a whole space of solutions called agents understanding designer's intent, right? Where the agents are model what the designer actually intended to write and not what the end actually sees. Like for instance, like the idea of like proxy rewards. So we have this formulation where we have a designer and an agent in a two-player interaction. And the bounded rationality of the designer, the human designer, actually implies that the agent what observed is not a reward, but it's a proxy reward. And one solution that we can do is try to have an agent that reasons about the designer's intention. And if all this like sounds a bit familiar to you, this is actually one of the tenets of the idea of inverse reward design that was introduced by Dylan Hatfield, Menel, and others in 2017, when there is this idea that when an agent actually can formulate the theory of the designer to reward, when starting from a proxy reward that the designer actually specified, and then use Bayesian reasoning to try to come up with like a theory of what is the actual reward that the designer tried to specify. And in the end, use this learned designer intent model to act in the environment in a safer way. But in our project, we took a different detour, and we come up with like this insight that, well, another way that we can reason in this space, in this interaction between the designer and the agent, is instead of like reasoning in the reward space, we can reason on the policy space, right? Because the designer, when writes the reward, also has in its mind, it's like in boundary rational mind, a policy sketch and a sketch of the policy that he expects the agent to implement out of like this reward. And we say, well, the key insight from here is that, well, boundary reinforcement learning agents might represent better models of the designer's boundary rationality, of the policy that the designer actually was intending to communicate. And it seems, and it seemed to us at least, that reasoning over the space of policies is a bit better because it's easier to scale via computation. If we get a proxy reward, we can generate like multiple hypotheses on what the actual policy was. And to do that, to model like bounded agents, we pick a page out of the book of like myopic optimization, where, well, if you actually want agents that can sort of like simulate this idea of like bound rationality, you bound the agent via reinforcement learning regularization techniques, with the caveat that generally in myopic optimization, we accept some of the performance drops that come from like myopic agents. And in our case, in the way that we thought about this problem, we are trying to avoid these performance drops that come from myopic optimization. And how we do that is we say, well, these are the kind of like errors we're interested on the specification, this error of foresight and abstraction. And well, they're really easy to model these kind of like bounded rationality problems using regularization techniques. Like we can construct a bounded agent or multiple bounded agents with like, for instance, different foresight capabilities by varying the discount factor, for instance, that the agent uses, or like, for instance, with varying the capacity of the neural network that the agent uses by, for instance, using techniques like dropout, Monte Carlo dropout. So with that in mind, we constructed this architecture that we call conditional boundary reasoners or optimizers, where we can actually have one agent that is able to model simultaneously via conditioning multiple solutions to the problem at different scale of rationality. It's a really simple modification of, like, for instance, in this case, not limited to this one, but in this case, to actor-critic architecture, like, for instance, PPO. And what we do here is like really simple. It's just trying to come up with like a bounded agent that can simultaneously have like multiple levels of rationality when it's acting. And the main, so far, the main use case that we have for this idea of like bounded rational agents, or at least that we tried, is this idea of safety via conditional bounded reasoners. And I'm going to show you what we have done thus far. And is the first thing we try is like, well, can we actually produce bounded agents via regularization in a sort of like systematic way when we get a single agent and the single agent is able to reason on all like these different bounded rationality conditions. And we use, like, for instance, as I said, the discount factor and dropout regularization to sort of construct a single bounded agent, a single architecture that can have different levels of rationality. As I show here, for instance, the stronger red is like the more rational agent, the agent without regularization. It's a single agent, but it's like the condition without regularization. And we can see that we sort of like in some sense, produce agents that have like different level, an agent that has different level of rationality by seeing how much it optimizes the return. And this is like by a minimal invasive modification to PPO. And we show that actually we can effectively build like this conditionally bounded agent that has the capacity to produce the optimal solution at the same time that producing solutions that are like a bit more myopic or a bit more bounded. And the other interesting thing that we got from this architecture is like, in some sense, we can scale at inference time. What we do with the architecture by conditioning on every state, for instance, that we're going to add in multiple rationality conditions and multiple rationality horizons, and then sort of like form a reasoning ensemble that first can act. We can always have like dictatorship, majority environment. But the other interesting property that we got was that, well, we can actually compute the disagreement of the reasoning on multiple scales and use that as metric to detect when the agent is over-optimized. In fact, for instance, in this example that I have here, you'll see on the right a scale of the agent during training that we are evaluating the disagreement between the different members of the ensemble and the maximum disagreement between the different members of the ensemble. And we found the correlation between the agent, for instance, getting a key on a really sparsely word navigation environment where the key was not actually specified as a reward. It was like actually really sparse. The agent only gets the reward at the end. And we see how in this architecture, every spike on the disagreement on the ensemble, or like trying to predict over multiple rationality conditions, actually allows you to detect when the agent is actually finding a solution that's due to like really over-optimizing or optimizing the long-distance consequences of the reward that it was given. That's one of the things that we did. So what can we do with this kind of architectures? There are things that we're thinking about to continue this line of work. The first one is like, well, we're actually thinking of how to close like this agent designer loop, how we can use this model of like human of designer bounded rationality built in the agent to sort of like model and plan sort of like in the IRD style. And then there are some other kind of like things that you can start thinking about. Like, for instance, can we meta learn the parameters of the designer? What's the human rationality in this case? Can we learn designer bounded agents? There's things that you can do now that you have an ensemble that a single agent, but that like behaves an ensemble with like different levels of foresight. Can you sort of like construct some form of like behavioral regularization to produce a scalable oversight? And obviously, because that's what we're using right now, we're thinking of how we can use and how we can embed these ideas into large language model post-training pipelines. And yeah, that was it. Of course, none of this would have been possible without the help of my advisor, my mentor, Michael Dennis, and the management from Jeffrey Hedinger, and everyone else on MATS has been like pretty kind and helpful during the past 2 months. So thank you so much. I'm not sure how much time is for questions, but here is a link to the feedback form. Feel free to shout there or anywhere, email. I'll be happy to chat about this at any time.
Great. Yeah, give it up for Manfred.